Hello and welcome to the Controller Talk podcast presented by Danfoss North America. Our goal is to bring you information about using Danfoss controls in the supermarket and warehouse industry, specifically in the US and Canada. We're doing these twice a month for now. You can catch these podcasts wherever you get your podcast, and it's also available through the Danfoss Ref Tools app. For the video version, check us out on the Danfoss North America YouTube page. Search for Controller Talk to see our video collection. I'm Dave Yoder, along with Chris Brown. Nothing in the coffee cup over there?
Nah, I'm empty.
Oh.
I screwed up.
That's a bad start.
It's a rookie move right there.
That's right. Hey, how'd those Maryland Terrapins do in their Duke's Mayo Bowl?
The bowl game was good.
Yeah.
Basketball team's tanking.
Oh.
Might have to find an indoor soccer team or something to pull for at this point because it's getting rough.
Kids flag football, maybe.
Yeah.
Hey, Penn State won their game.
They did.
It's only the Rose Bowl. No big deal.
Yeah. I think I've heard of it before.
Yeah, that's right. So, but you don't want to talk about football. Clearly.
I'm still in the recovery period.
Oh, yeah. Sorry. Yeah.
Touchy subject.
Okay. We won't talk about the Ravens, at least this time. Hey, since this is our first recording of the new year, let's go tackle a topic head on that sometimes confuses people that are setting up or troubleshooting things that use a variable output, like a variable speed compressor, digital compressor, or even variable speed condenser fans. You know, there's lots of other uses for the variable output, but we're going to focus on those today. So some people call them analog outputs too. They normally send a variable DC signal out of a board to a device in the range of 0 to 5 volts, 0 to 10 volts, or 10 to 0 volts.
Yep. Yeah, we'll start on the compressor side. So within the compressor section of the system manager programs, historically, we're using these for things like a variable frequency drive, so VFD, and we're controlling the speed of the compressor to try to modulate to the suction target as best we can. So it gives us a little more capacity control than maybe just staging compressors and unloaders would. So that's historically why the option was initially introduced into the system managers. And then in the last 15 years or so, we've seen more of a shift to digital compressors. I won't steal the thunder on the manufacturers from you, but I think most guys, if you're listening to this podcast, you've probably seen them, heard them, come across them before. We're dealing with these digital compressors where you're cycling unloader solenoids at a pretty frequent rate. And for us, using this VO option in our program gives us that ability to do that.
Right. Yep. And if we're talking about variable frequency drives, then they can be abbreviated VFD for variable frequency drive or VSD for variable speed drive. But some people like to use different nomenclature for those. Sure. Or just drive. Yeah. Any of those. But yeah, that's right. In the controllers, there's been this option in our controllers, it's always the first compressor has an option. If you want to use the inverter option there, one of the things you can do is set it up for a VO, which was intended to give you a variable output for a variable speed drive. And then you get a bunch of things that go along with it. Yep. But when it comes to these digital compressors, they're usually made by either Copeland or Bitzer. And typically, Copeland will use a 1 to 5 volt DC signal that goes out to their module to cycle that unloader on the compressor. And this can be for a reciprocating compressor or a scroll compressor. And then you have to pay attention to the specs on the compressor and that module that they're using. I think they sometimes call that an IDCM.
On the Copelands, yep.
Yep, okay. But you have to know what voltage range they're looking for. A lot of those use a 1.44 volt DC minimum. So in our controller, on a 0 to 5 volt scale, we set the minimum to 30% so that you end up with a 1.5 volt minimum, because we don't want to drop below 1.44 because then it'll tell the compressor to shut off.
Yeah.
And yeah, go ahead.
That's a little bit of a tricky subject for us. Just when we don't call for the compressor, that signal, that voltage goes away. So that 1.44 minimum's not relevant to the program anymore. We're kicking out 0 volts if we've dropped below suction target. That IDCM does trigger the contacts on it as if there was an alarm for a signal loss. So
Okay.
I think that's something for everybody to keep note of, is the those alarms may not be legitimate coming from the IDCM, the alarm light, and the contact, because it could just be we're just not calling for the compressor because we don't need it.
Right. Typically, you won't see that because there's always enough load there that it'll call for it. But there are ways around it. We've done some kind of special programming.
Agreed.
So that it doesn't fall below that. But for the most part, you're going to see 30% as the minimum, so we don't fall below 1.5 volts. And then, of course, we set the 100% maximum at 5 volts.
Yeah.
So that everything lines up. There is a startup percentage option. What we found is that some of the delays can affect that a little bit, meaning you're always going to get this startup percentage so that when you do start, you start at a certain percentage of how many times you're unloading. But some people like 100%. Some people are okay with 75. Some people are okay at the minimum. But it's kind of customer driven.
Yep.
And a lot of it has to do with oil, that sort of thing. But some customers like 100%, and then you're safe. And then from what I've seen, it tends to hold at that startup percentage for 12 to 15 seconds. And then
it'll start to ramp.
And then it can either drop back or speed up. That's right. Yep. Based on the load. But yeah, you have to check the Copeland module part number, because different part numbers on those modules will have different voltage ranges that you want to use. But from what I've seen on the Bitzer, they typically have that 0 to 10 volt signal going out to a Siemens module. But those are usually 0 to 10 volts, but you have to kind of look at the paperwork.
Yep. And so another aspect of this setup is you're getting more than just the analog output when you enable the VO signal for the compressor in the program. So obviously you're getting that 0 to 5 or 0 to 10 analog output that you're going to wire to the compressor module. But the way that the options were introduced in the program, going back to it originally being linked to a variable frequency drive, is you get some secondary things too. So there's a run relay, a reset relay, and a bypass relay that the controller assumes all those things are part of this setup. Even if you don't physically have them, there's nothing wired to them. The program assumes they're there, and we'll get into a second in how you have to treat that. And then on the input side, it assumes that you have physical wiring from a proof and a fault coming back into a point on an input board on the controller as well, to get some feedback on, again, assuming it's a drive, that it's actually running and that it's running when we want it to. So you get those few additional points that maybe guys, if it's the first time that they've used this option or are troubleshooting these a lot, they may not even know they're relevant, but they're very relevant in how the controller is controlling that analog output signal to the compressor module. So and linking that again to the Copelands and the Bitzers, these are basically, they're not there ever in terms of actually having a physical point. The program needs to think all these things are being used normally. So at a minimum, it needs to think that the proof and the fault are in specific states. So it wants to know that the proof is in an on state and the fault is in an off state before it's going to allow the compressor to run and start to modulate the analog signal. So guys kind of tackle that in different ways. Some guys will just put in an open point that physically exists but has nothing wired to it, and just put in a jumper so that they can ensure that the proof and the fault are always being looked at in the state that they want it to. Some guys will put in fake points, or dummy points we call them, and then they can manually override them through the program so that they go into the state that we need them to go in. That one's just a little more maintenance maybe, because if you ever do a software upgrade, if the database is reloaded somewhere down the line, then those are things you'd have to circle back to and put in place again, or else you might end up in a spot where the analog output's not functional until you take care of that. You'll come across a status sometimes, especially if these things aren't necessarily in the right spot to start, where you can see inverter off for the status in the program. That's just a reflection that the algorithm needs to restart, probably again because of one of those lockout conditions. and you just want to restart the algorithm, that could just be as simple as restarting the controller in that case.
Yep. One of the things you can do that I've done, and you probably have as well, is if you have a fault input to play with, normally you want that to be off, but if it does say inverter off and you turn the fault input to manual on for a few seconds and then put it back to off, that will restart the algorithm. And then typically the first thing it does is it has to go through its delays, but it looks at the fault to make sure it's off, and it looks at the proof to make sure it's on, and then it'll start up.
Yeah.
And then you're good to go.
And bypass and reset relays, the same applies there. I didn't really specifically state that, but normally if you just leave those as zeros in the program, if you don't have them, it may not cause issues, especially not right away, but there's the potential there for it too, in case something ever were to happen with those proven faults. So I normally like to stick some fake points in for the bypass and the reset.
Okay.
So that you don't get stuck in a tough spot there.
Yep. So the good news about all this, with this extra fluff that you have to put in to get the compressor running, the good news is that in the latest version of our latest controller, so we're talking about the system manager, the 800A, there is a software package called 3.2.6, and it actually has a working option for the digital compressor. So that means that instead of picking VO, you can go in and pick digital compressor, and then it just gives you an analog output point, and that's all you need. You don't get the extra relays and inputs.
Right. And that option's been there for probably close to 6 years now. So
yeah,
just be careful. If you see it, that doesn't automatically mean you can use it. You want to make sure you got that version that you set in there before you do that.
Yeah, you can pick it as much as you want, but it's not going to work,
right?
Unless you're on a 800A using that latest version. And from what I've seen, some guys are doing upgrades now, and if you have one set up and it's under VO and your digital compressor is working, and you're like, okay, I'm going to clean this up and switch it to a digital compressor, you would expect that you're going to have to put the compressor point back in, put the name back in, turn the history back on for it, and then the controller will take about 10 seconds for it to kind of update itself and then start sending your voltage back out on that point.
Yep. Yeah, that's where I was going next. Make sure you jot that point down before you change that option, or else you're going to be fishing for it.
Yeah. We've been together too long. It's already in my thoughts. I'm scared.
Let's see if we're thinking the same on the condenser side too then.
Okay.
So yeah, we'll switch gears and kind of finish up with the compressors there, and we'll get into the condenser section now rather. So here we're still talking the analog outputs or variable outputs, and what are we sending the signal to? It could be a number of different options, really. I mean, you could have your traditional one variable frequency drive set up. Some guys will have a bypass panel in play there, which is helpful with some contactors to wire to. But that's maybe the more typical option going back years and years that we used to see. And then you can get into some other more recent options, a mini VFD, which would be a one per motor setup, maybe a pair per motor, one small VFD per pair of motors. We see a lot with the ECM motors these days. As expensive as I hear they are, people are still using them.
Yep.
On that side, it's normally we see just 0 to 5, 0 to 10 volt signal, whatever that is, jumped to a point on each motor of each fan, and controlling the condenser fans in that fashion. And then we do see some setups where it's the condenser split in two, just almost like the split valve treats it. And we've got one analog output that's going to all the fans or motors on one side of the condenser, and then a different analog signal that's going to the second side. And it's usually just kind of replicating what the first side is doing, but it's taking the split valve or the split relay into account, so that when we're in split, we're just dropping that second side to a 0 volt signal to turn those fans off. And then similar on the digital inputs, as we were mentioning with the compressors, when you enable the VO option for the condenser section, you're going to get proof and a fault. You get is it enable, bypass, and reset? I know it's at least bypass and reset. I think you might get a third relay too there.
Like a forward run.
Yeah, yeah.
Yeah.
So you're going to get those same points, and so if you're using the bypass panel and have all of them, then that's there for you. But if you're not using that, then kind of similar sentiment to what we were mentioning before, where having either hardwire jumpers or using this fake point setup that I was describing before, you want to apply those same things here, or else you can get into the same spot where it's locked out or it's just not generating a 0 to 10 volt signal to go to your fans.
Yep. You can always alarm on the fault input if you have one, and that'll tell you, hey, you're in fault. But otherwise, you could go into fault and not know it, and you happen to look at your condenser status and it says it's in bypass, and you really have no idea how long it's been that way.
Yep, and see it all the time.
Okay. So if we're talking about the HVAC blower fans, then you could have a drive on the fan, and I haven't seen ECM motors that big just yet, but maybe someday, if there's enough, if they are affordable at least. But yeah, you could have a VFD on the fan, and it's good to have fault and proof inputs if you have all that, and then you can reset it remotely because it'll give you the option on the screen to do that. If you're using fan proofing, then that's basically you want your input to be able to say, hey, my fan's up and running. So you have to make sure that if you're at a minimum speed on your variable speed fan, that it's still going to be able to make that error-proof point. So it could be a sail switch, it could be a pressure switch, or a current sensing relay, but you have to test it at minimum just to make sure it doesn't assume or kind of give you an idea that you lost your airflow just when it's at minimum.
Yep.
So yeah, and this is not quite as common as it used to be, just because a lot of the rooftop manufacturers now are shipping them with their own self-contained controls, and there's a little drive in there that we don't control directly, but there might be some other device in there controlling all that.
Yeah, and we don't really get into it much here, but I mean, the miscellaneous section has a part where you can set up variable outputs.
Yeah.
You're not going to get the PID type of logic that you're getting with what we're talking about here in these other three sections. So it's a linear scale, whether it's pumps or whatever else you might be getting into, or you're looking for some options. That section's there, but just be aware of that it's probably going to overreact to what you're looking for, depending on what that setup is. Yeah,
you always need a analog type sensor to drive those miscellaneous variable outs, or you need a calculation.
Yep.
Yeah. Okay.
So, I mean, all of this, especially the condenser section, is probably where it comes up a lot in conversation for me. But why are we worrying about all this going to analog outputs? Why aren't we just turning it all on and off, right? It's simple. Let's do it.
Keep it simple.
Yeah. So we've got something called the cube law, which applies to fans, pump speed, and it's related to the speed versus the power that's being consumed by these pieces of equipment as we modulate them up and down and speed them up and slow them down. So, I mean, just for reference or example, if we take a fan and slow it down from 100% of its max speed, go down to 80%, so a 20% reduction in speed, that results in a 45% reduction in the power that it's consuming. So there's a exponential gain in your power versus your speed by slowing these down. So, I mean, even just going from 100% down to 90%, so you just reduce it by 10%, then you're still reducing your power by 27%. So it's big energy gains, which is what we're always fighting. We know the refrigeration systems are the biggest energy consumers in a building, typically, for these grocery stores. So this is one of the spots that we look at to try to save some energy by offering these algorithms in the controllers.
Yeah. Yep. Back 15, 20 years ago, the sales guys used to say you can't argue with math. And so they would refer to these laws as the reason.
Guys find ways to do that today.
That's right. So you could also call it the affinity law, that the power needed is proportional to the cube of the speed or the flow. And it comes from some basically laws that some smart people came up with long ago.
The college textbook on it somewhere, right?
That's right. Yeah, check your basement. And then, of course, we had to throw a shameless plug in here that I did a little research and checked a few different places on the internet, and I found it on the internet. So you know what that means.
You're showing off. That's what that means.
It means it has to be true. But a couple different sources did confirm that Danfoss was the first manufacturer to start mass producing three-phase drives in 1968.
There might be some on eBay if you look hard enough.
Probably is. There probably is. Yeah, that was the first company in the world to do that.
That's cool.
Which was pretty wild. I was just a kid back then. Yeah, just a babe.
That makes one of us.
That's right. Yeah. You were a long ways from that.
Yeah.
All right, Chris. So now that we've covered all this analog output stuff, we're going to see what kind of questions you can output, or answers anyway. I'll do the questions, you do the answers.
Might be a new year, but this is not going to change.
That's right. Yeah, I found some good ones here to torture you with.
Thanks.
So, the question, or the option here is to try to answer something, and that's why I try to call this Stump Chris, because if I didn't stump you, it'd be no fun. So, so I have not shared the question nor the answer with you. Today's question does have to do with drives.
Uh-oh.
And you're sweating already.
Yep.
It's not even that warm in here. So what was the name of the first drive that Danfoss produced?
Are we like a model type of format we talking?
Yeah, let's go with a model name.
Give me a lifeline here.
Let's go with a model name just to narrow it down.
Ooh. AKD was probably not in the... Yeah, so we're... VLT used to go back... Let's go with a VLT 100.
You know, you're pretty close.
Yeah.
In the grand scheme of things, you're pretty close, but you got to think smaller.
VLT 1?
You're even closer, but now your guesses are up. So It was a VLT 5. Yeah, that was the first one. Did you ever see a picture of it?
No.
It's big.
Yeah, I can imagine.
Yeah, it's almost a cube, 3 feet in each direction. Yeah.
What was the, did you say anything about the application?
No.
No,
it's just to look at.
Yeah, okay. I wonder what they were using it for.
Yeah, probably running a pump for water, or, milking cows or something. Who knows in that time. Yep. So, you got half credit for that one because you came up with VLT.
I at least put some thought into it, I'll say that.
Oh, that's right. Okay, now we got a follow-up question for you.
All right.
Where did the term VLT come from?
Oh, Jesus. I had a better chance at the first question. Where did the term VLT come from?
Yeah.
I can't even venture a guess.
No, not going to take a stab at that one.
No.
So the Danfoss guys at that time were like, they built this box and they proved it worked. Now they had to come up with a name for it. And they came up with Velotrol. Velocity, load, and torque, or something to that effect, and they were pretty happy with that. But the problem was there was an English company already using that name.
Yeah.
So they debated back and forth, probably over beer and pickled herring, and they came up with VLT instead. They just shortened it.
You know how long I would have sat here trying to guess that, right?
We can't afford that much studio time.
No.
All right, so let's move on to listener mail since we have successfully stumped you. This is one for you. I think you can answer this. You remember that Bucky in Baltimore was, asking us questions last year?
Yep.
Well, his cousin Butchie is up to bat now. He's got a question for us.
Sounds sketchy.
There's lots of Butchies in Baltimore, in case you don't know. He wants to know how important that RPM number is when you program that into the controller.
Doesn't mean anything.
You can't say that.
It is primarily just for visual usage. It's not being used in any algorithms or logic. It's literally just taking whatever scale we have as far as 0 to 5 or 0 to 10 volts.
Yep.
And looking at that over 100% range and applying that number. So if you're set for 1,000 RPMs and we're at 10 volts and 100%, it's going to show 1,000. If we're at 50%, it's going to show 500.
Right. So it's there. It's always good if you can plug that number in and it's accurate to the motor.
Yeah.
But if it's off, it's not going to hurt anything.
No, and that's it. It potentially causes some issues just because somebody looking at it might think something's wrong if it's not programmed right.
Right. Yeah.
But in terms of the output, you want to look at kind of the raw value there and just pay attention to your percentage or your voltage and go off of that if you're troubleshooting.
Right. Okay. Well, you nailed that one. Very good.
We should have started there or end on a good note. Maybe that's a silver lining.
That's right. Yeah. Ending on a high note.
Yeah.
All right. Well, for our listeners, if you'd like to drop us an email with a suggestion for topics to cover, a question or a comment, you can always email us at ControllerTalkNorthAmerica@danfoss.com. That's ControllerTalkNorthAmerica@danfoss.com. Thanks for listening. Our studio and video engineer is Michael, don't call me Mike, Beckerman. Our audio engineer is Raul Garcia, this time in the flesh.
He does exist.
He does. There's a little less mystery right now. Maria is back from Europe, and she's, of course, the real backbone of this operation. And the new guy, Josh Tignall, well, he's already missing.
Who?
That's right. Until next time, for Chris Brown, I'm Dave Yoder. Stay cool.